Hello, my name is Chris, and I'm going to talk about the object pool pattern today, specifically how you can use it for slab memory allocation, which is a really useful tool. So what is the object pool pattern? The object pool pattern is a pattern where you perform initialization of objects at one time, and then you put them into a pool. Then when a client needs an object, it can retrieve it from that pool, use it, and when it's no longer needed, it can be added back to the pool and hopefully reset to some initial state. These objects can be reused instead of using costly allocation and deallocation operations. Here's a basic outline of how it works. You have your pool of objects over here and your client over here. So if the client needs an object, it can pull it from the pool of objects, and then the client can use it for whatever it needs. And when it's done, it can be returned to the pool for someone else to pull out at a later point in time. Now, why would we bother to do this? Allocation and deallocation take time. They are costly operations to perform frequently. Um, and so we want to cut down how many times we're doing that by reserving these objects in a pool. Um, Now, if we go into the slab allocation of memory, which is the coolest part about this, you can reserve your memory so that another process can't take memory that you know your process will need at some point in time because you already have allocated the objects even if you're not using them yet. And it allows you to keep your program's data in contiguous memory, which can reduce cache page misses. Um, and that's really the big strength of slab allocation is you can reduce how many cache page swaps you have to perform. And cache obviously runs faster than RAM, so it's good. Here's a very simple UML example. So we have our pool object over here, and then whatever object fills the pool with whatever its data and methods are. We have an array of the objects, so that they're stored in contiguous memory, and an array of booleans tells which ones are currently in use. And then I thought throwing in a next index to know where in the pool to start looking for a new object would be a useful thing, so it's thrown in. Um, the main functions you need are the first two here. You need to have one that will get an object from the pool, and you need to have one that will return an object back to the pool. This third function is more of a helper function that you can set up in order to reset the objects back to an initial state. Because when you pull from the pool again, you want to make sure that everything is the way it should be initially. Now, there are some consequences or drawbacks with this. Objects may not be returned to the pool in their initial state, which means the next time it's pulled from the pool, it could be used incorrectly and you could get wrong results. If a pool fills up with these wrong states called stale state items, um, then the pool is called a cesspool of objects. If care is not taken, multiple threads could request the same object, and then you'll have issues where both threads are racing each other to write into this object. And obviously that'll give you incorrect results. The program will always consume at least as much memory as the size of the pool, even if none of the objects are in use. That could be seen as a good or bad thing. These days, with memory being pretty cheap, I don't think it's that bad anymore, as long as you will use that memory at some point. Um, and supposedly, in garbage collected languages, it'll take longer to check through to see if there's anything to clean up because the collector needs to check all references to make sure everything still has a reference to know if it needs to clean up something. And lastly, your pool has a limited size. So unless you implement some method for expanding it, which would probably be pretty costly, you're stuck with whatever size you initially designed for. So why would we use this? Real-time applications, such as games, um, they require that execution performs very quickly. Allocation and deallocation just takes far too much time to be wasting when you need to make many frames happen in a second. You could also use it for thread pooling, where you initialize a bunch of worker threads at the beginning of execution, and then as work comes down the pipeline for them, you can feed them straight in without having to initialize a thread, which again is a costly operation. And you could also use it for pooling database connections. After the connection is created, you can, and you no longer need it anymore, you can put it into the pool where you can then pull it out instead of having to reestablish the connection between the client and the database over and over again. So now we'll move on to my simple little example. We have an object, which my object just takes up 100 integers of space. And then we have our pool. So I'm only using a pool size of 5 so that we can just see what's happening easily. Here's that array of objects like I was in the UML, and the array of booleans and the next index to look at. So I initialize the in-use booleans to false, and then here's my getObject function, where I basically just step through until one isn't used, and if they're all used, then I return null, and then I return whichever one is unused. And then the return one, I check that that the address is in the right range, and then I set it to false if it is. So my test is going to be initializing a pool, requesting 2 objects, and then returning one of those objects back to the pool. So let's see what happens. All right, so we initialize the pool, and the status is that none of the objects are in use. Then we requested 2 objects, so 0 and 1 became in use. And then we returned the first one back to the pool, so now it's no longer in use, but object 1 is still in use, and the rest are not in use.